All right, so last we talked, we had introduced the concept of a Turing machine. And if this will actually launch, there we go. We took a look at a visual for our first Turing machine program. So we defined these three transitions. We defined the Turing machine with these rules, these transitions. We had AA on the tape prior to the start of the Turing machine program. And we note that it always starts in state Q. This should be sub-zero with the read-write head under the leftmost character. In this case, it's the A. And then from there, we just follow the associated transitions that we can make according to these rules. So if we're in state Q0 and we see an A at the current position, that tells us to stay in state Q0, write a B to the current place on the tape, and move the read-write head one space to the right. So that's exactly what happens between this first image and the second image. We rewrite an A to a B, and we move the read-write head one place to the right, staying in state Q0. Then we're in exactly that same state when we see this A. We're in state Q0, and the current position on the tape is an A. So we rewrite it as a B, and we move to the right, staying in state Q0. Now we're looking at a blank. The current symbol that we're looking at is a blank. So we are in this last case. So in state Q0, when we see a blank, we're going to transition to state Q1, write a blank. So we're going to replace the blank with a blank. So no op, and we will move left. So we see at the very end of this, we're pointing back at the last B. We're in state Q1, and we're done. There's no move that is defined for this. We're at a final state, so we can terminate. We go into that halting state that we talked about. Questions on this example? We kind of rushed through it a little bit at the end of the last class, but if anyone has any questions, I'd be happy to answer them. Okay. Transition graphs. Can we visualize a Turing machine as a transition graph? We can, and I don't really like to. It's kind of the answer that I end up with here. So here's a transition graph of the last Turing machine that we just covered on the last slide. So we see that we have loops from Q0 to Q0, and now just like with the push-down automata, each edge will have three labels on it. The first is the read character on the tape. The second is the write character to that position on the tape. And the third is the move that the Turing machine is going to make. So if we see an A, replace it with a B, move right, transition to itself from Q0 to Q0. If we see a B, replace it with a B, move right. Notice how this doesn't really give you the same level of ease of understanding, I guess, as kind of looking at the tape does. I find looking at the tape to be much more intuitive, and it's a little bit easier to figure out exactly what this Turing machine does by thinking about it with the associated tape there. But if you're striving for a program to write a Turing machine or something of the sort, then you'd want to think about it and emulate it in terms of this transition graph. That would be a much better internal representation of a Turing machine than anything else we could come up with. Questions on what this transition graph says or means? Yeah.
Before you mentioned that this Turing machine setup has might have a stack. Does this one have a stack, or do we?
It has no other storage. Okay. It only has the tape.
It just has tape.
Okay. Yep. We could emulate a stack with the tape. We could emulate a cube with the tape. We could emulate anything else that we want to with the tape.
Slow down there. We're gonna.
But yeah, we don't carry any other storage. The tape can do anything that Java can do, or Python can do, any modern programming language we can do with just the tape. It is wild. Any other questions? All right, let's take a look at an example transition graph. All right, we have a transition graph. Assume the tape is A, B in that order. The read-write head is pointed at the left A. Think about, what does this machine do? Here's the transition graph. So on the tape is AB, the read-write head is pointed at the A. Go ahead and see if you can step through this transition graph and see what it does. Give people 30 seconds to find it. Who thinks they see what this does? What does it do, David?
Goes back and forth.
It goes from Q0, reading the A, right to Q1. Now there's a B, it reads the B and goes left back to Q0.
Does nothing.
And then it reads the A and goes right to Q1. And then it reads the B and goes left to Q0. And then it reads the A and goes right to Q1. It's an infinite loop. It's not going to write anything meaningful on the tape, but it's also never going to reach a halting state. Even though we have things that would halt this machine, there's nothing about that input that is going to halt the machine. So it is possible for a Turing machine to enter an infinite loop. As you would expect with anything that can emulate what you can do with a programming language, if you can write an infinite loop, then it is possible to create a Turing machine that goes into an infinite loop. Which is kind of it creates a very interesting problem that we'll analyze a lot more in detail in a bit. And we talk about complexity and solvability, stuff like that. Seem to have not quite done this correct. All right, we also, just like with pushdown automata, can represent a Turing machine via an instantaneous description. So remember that the difference between a transition graph and an instantaneous description is that the instantaneous description is working with a particular example, something that's on the tape. So we need some way of showing what is the state of this Turing machine without leaving out any information as concisely as possible. We want some notation that tells us, here's the current state of the Turing machine with this tape. So we need the current state of the control unit. That's very important. Is it in Q0 or Q1 or Q2 or some other state? We need access to the contents of the tape because that's very important to know what the Turing machine, where the Turing machine is. What's on the tape? We also need the position of the read-write head. If there's any part of the tape that is unspecified in this instantaneous description, it's assumed to be blanks. So here's an example of what the tape might look like. We have character A sub 1 written at position X sub 1. We have A sub 2 written at position X sub 2, nothing specified for a while. And then we have A sub K minus 1, A sub K plus 1. The internal state is Q with the arrow pointed at A sub K. So just the current position, and we have the first written character that we care about, everything else is blank. The last written character, everything else is blank. So if we were to write an instantaneous description of this, it would look like this. And we zoom in on that so you can actually see that text down there. So you can draw it kind of in tape form, but that's also quite verbose. There we go. So you can see that we kind of have this concept of X sub one. Q, which is where the read write head is pointed, followed by X sub two, which is the. Part of the tape where the read write head is and everything that's after it. So we have everything before the read write head that stops here. And then everything after the read write head, so we would have this entire sequence. Followed by the state, followed by everything at that position and after, does that make sense? So if we write that out, we would end up with A sub one, A sub two, everything up to A sub k minus one. Then we have the state that the machine is in, followed by everything at the tape, on the tape, at that position and after. So that becomes the instantaneous description of a Turing machine. That's everything that you would need to know to be able to kind of ground yourself in a particular instance of the Turing machine running on a particular string. Yeah,
So just be sure, is each cell in that Turing machine like a states queue? Like, are those all states?
no, they're all characters on the tape.
Okay, so when it says
Q is the internal state. It'd be like Q0 or Q1. We don't need to know what all of the possibilities are for the Turing machine in an instantaneous description. Think of it like taking a picture of the Turing machine. It's like, here's the current state, here's the current tape. That tells you everything that you need to know about where the Turing machine is right now.
okay,
Yeah. That clear to everyone? Any other clarification questions? So now how do we describe transitions? We can go from one instantaneous description to another instantaneous description via one of the transition rules. Just like before, we have the turnstile symbol that represents we can get from one instantaneous description to another instantaneous description via some legal transition. So here's one example. We have a transition rule from Q1 on reading a C on the tape. We'll go from state Q1 to Q2. We'll replace the C with an E and we will move right. The tape contains A, B, C, D, and the read write head is on a C. Let's see if we can figure out what that transition looks like. Go ahead and write the instantaneous description transition. So you'll start with one instantaneous description, the turnstile symbol, and then another instantaneous description to go from the snapshot that is here and then the snapshot that's defined after we follow this transition rule.
is there an example on one of the previous slides that we could look at, what the syntax looks like?
So we know that it's gonna look in this form where we have everything on the tape up to but not including where the rewrite head is. Then you're gonna have the name of the state that it's in, followed by everything that is after. So let's just write the first part of it.
Is drawing the tape part of that, or is it just?
Yeah, you can draw the tape, but I think the string representation is cleaner and easier. It communicates the same information. So if you get it down to its string form, you can, if you know what that represents, you can construct the tape in your mind. And that way it just takes up less space.
Okay,
So what would the first one look like? Let's just draw out the first instantaneous description. We want everything on the tape up to but not including where the read write head is pointing. What is that? We know the string is. I think it said A, B, C, D somewhere, right? Yeah, it says it right there. The tape contains A, B, C, D. So basically, if we were to draw out this Turing machine, we would see that we have 4 relevant cells that contain A, B, C, and D. The read write head is pointed here, and we're in state Q1.
So,
Yeah,
so it'd be ABQ0CD.
I think we're in Q1.
Oh,
But
Q1.
basically, yeah, we want to, the string is A, B, Q1, C, D. So that's the instantaneous description of this. And you can see how this string maps precisely to this image. Because the Q1 occurs after the B, which means that the Q1 is pointed at the cell after the B.
And you said afterwards.
Yeah, so we want to now, from this, go through this transition rule. So we're gonna have the turnstile symbol. And then we need another instantaneous description for what the state of the Turing machine is going to be after we take this state and apply that transition. What do we get?
ABEQ2D.
A, B, E, Q, 2, D. So this transition is basically saying we start at state Q1 pointed at the C. If that's the case, then we move to state Q2, right, and E at the current position and move right. So if we were to draw this out, the new tape would be A, B, E, D, pointed here in state Q2. So if we take this idea and transition it to here, we see that we want A, B, E followed by the state Q2 followed by D. Looks right to me. Is that what everybody else got? Excellent. So just like before, we can specify how instantaneous descriptions turn into other instantaneous descriptions via the use of transitions of some kind, which we can write very easily with just the turnstile symbol. It represents a very complex idea. It says we can get here from here via some transition rule. Which means that you also don't necessarily have to specify the transition rule if all you care about is something like what are the associated states of the Turing machine as we read this particular input. What happens? What are the associated snapshots? Think of it like stepping through a program using a debugger. You can look at every single state as a snapshot of the program, what's exactly in memory, what are all of the values of all of the variables at every line of code for a particular input or a particular run through of that program. Is that always going to be the case? No, maybe you provided some different input. The user provides something else to the program and that causes it to run differently. It's the same for a Turing machine. You put different things on the tape, it's going to have different sequences of transitions and different instantaneous descriptions based on what's on the tape. But this is kind of like the debugger, where it shows you these steps or the states that it goes through as it goes from its initial state to its halt. There's an eraser here somewhere, I swear. Where'd it go? Someone stole it. Anyone see an eraser anywhere?
No.
All right, I'll watch my hands.
You know.
All right, so there's the answer. It's exactly as we specified. So here's the next thing. Is it going to be possible to produce a set of instructions that puts a Turing machine into an infinite loop? This seems like a good question to be able to answer about any Turing machine, right? is there a way that this Turing machine could enter an infinite loop? We will actually come back to this, yeah.
I was just gonna say, if it does everything that we can do in Java and other languages, then yeah, 'cause we can.
Well, you can also write a program in Java that has no way of entering an infinite loop. So the question is, for a particular program, a particular Turing machine program, does there exist an input that would put it into an infinite loop? It'd be the same thing like saying, here, I give you a program. Is there an input to this program that causes it to go into an infinite loop?
Depends on.
Exactly, yeah, well, we'll come back to this problem to be able to study it in more detail when we start talking about computability. And it ends up having some very interesting results when we study it. But think about the logic that you would go through when looking at a program to say, is there a particular input? And then think about doing that from the computer's perspective. So not using your amazing brain to figure it out and use critical thinking. But would there be an algorithm that regardless of the program you're looking at, you could answer, yes, there exists an input where this goes into an infinite loop, or no, there is no input that causes this to go into an infinite loop. It's an intriguing question. Maybe it will bother you as you go to sleep one of these nights, probably not.
Give it to my sister, she'll find a way.
But we'll come back to that. I just kind of leaving that as a breadcrumb of something interesting using this that we can think about.
I'm sleeping.
So we've talked kind of about just how Turing machines work in general. It would be nice to think about how can this work as a language acceptor. The way that we saw how we can accept regular languages through DFAs or NFAs, we can accept context-free languages through NPDAs. What does a Turing machine language acceptor look like? So we need to make some assumptions before we can do this. The first is that the string that is going to either be yes in the language that is accepted by this Turing machine, or no, not in the language that is accepted by this Turing machine. We assume that the string is written on the tape. Blanks are on the tape everywhere the string is not. The machine needs to start in its initial state, so probably Q0. And the read-write head is going to be positioned at the first character of the string. If these assumptions aren't met, we can't guarantee that it's going to be able to read the string. You couldn't program a generic Turing machine that says something like, go find the first character. I suppose you could say, go find the first character, but that becomes unnecessary if we make these assumptions. So we accept, if and only if, Turing machine reaches a final state and the Turing machine has halted. So there can be some transition out of a final state. Or we can also transition from a final state to the halting state. So it's no longer good enough to just be in a final state like it was before, because we're not just parsing the string once from left to right. We could be moving back and forth. We could be moving and writing to parts of the tape that didn't have anything on it before. We have full power of this. So in order to terminate, we also now must transition to a halting state. That becomes the real final state or accepting state. It's basically saying program over. If you wrote a program that could say something like yes or no, you pass this course or don't pass this course, you don't want to stop early. You can't stop after week 3 and say, I passed the course or haven't passed the course. Even if you are currently passing, that does not necessarily mean that at the end of the course you will be passing. Or if you're not passing, by the end of the course, you will still not be passing. You must reach a halting state, which only happens once final grades are submitted, and then you know what your final grade was. Up until that point, there's some planning meaning to your grade, but it doesn't necessarily, there's no real meaning. The grade at the end of week 3 doesn't go on your transcript.
What
One other thing to note, we don't allow blanks in any portion of the string. That will mess up a Turing machine program.
You use blanks as part of the parsing of the string though?
Yeah. Yeah, you can create blanks there as part of your program. Maybe you want to do something like split the A's from the B's and A to the N, B to the N, and have a blank in between them. You could do that. You just take the first B and move it to the end. So we just don't want there to be blanks at the beginning.
Oh, so it's fine to have blanks at the end, just not the beginning?
And yeah, before the string begins, all blanks. After the string ends, all blanks. As we're processing, we may write some blanks in the middle of the string. That would be okay, but we want to assume that there are no blanks when we begin, because we don't want to have to handle that logic.
Okay,
It's unnecessary logic to handle. If we're trying to have a string, there's not going to be, there's no blank symbol in a string, like A to the N, B to the N. Where would a blank go? If we wanted to put it between the A's and the B's, that's a decision that we, as the Turing machine designer, make, so it should be a rule. But generically, we don't want there to be any blanks in the middle of the string, because if that was the case, you read the string from left to right, or you're in the middle of parsing the string, you see a blank. You want to know I'm past the end of the string, not there might be some more stuff out here, in which case you'd have to look forever to one side to ever be able to be sure. And now our program would never halt, because we'd never know if there was another part of the string out there somewhere we just hadn't gotten to yet.
okay, do you have to designate a special character for like a space character? If you were reading, for example, like a sentence where like the dog runs, you have
Yeah.
a space between the words.
So you can imagine doing something like putting the ASCII character or the ASCII symbol for the character there, and that way the blank is distinct from the space character.
Okay,
So yeah, whatever representation you would need to differentiate the blank from something that might look like a blank, like the carriage return or the new line or something like that. So this was mentioned already, but if we allow blanks, the machine would never know where the string actually is. So we'd have to look at the entire tape. And since the tape is infinite in both directions, we'd never stop. If the string on the tape is not in the query language, we have two ways that we can fail. We can halt in a non-final state. So if we reach a halting state and stop without being in a final state, we reject. Or if we enter an infinite loop and never halt. Although recognizing that we are in an infinite loop is itself an interesting problem. So an infinite loop is said to be a rejection if we have a way of proving that we're in an infinite loop. Questions on any of this logic? Yeah,
Two questions. One, have we seen, like, is there any like definition or like a way that we can see we're in a halting state? Like, have we seen that as an example yet of a halt or?
yeah. So when you move to a state, you can be like QF
Oh,
to halt. Yeah, it's a special state that you can move to from any state if you define a particular transition, or if no transition is defined, you will also move by default to that halting state.
okay. And then. So we're the ones who are like, quote unquote, programming this Turing machine. So we can see how there is a loop. But I had thought like in certain things, you can't prove loops.
Correct.
When you're in a loop, like no machine can tell itself like, I'm in a loop.
Right. We'll come back to exactly that problem momentarily. If we're in an infinite loop, there's no way that we're going to accept. So by default, we reject. It turns out there's a whole different class of language. We call this decidability versus undecidability. In a decidable language, and we'll come back to this. Let's give you an overview of the definition now. A decidable language can tell you in a finite amount of time, yes, we accept, or no, we do not. An undecidable problem can tell you, yes, we accept in a finite amount of time, but there exist inputs where we spin forever on a no. So we can't decide yes or no. The Turing machine will halt if the answer is yes, but it's really difficult to answer the question, is it no? Because we just don't know if we've halted yet. Is it going to halt sometime in the future? How long do you let it run? there will be some examples, some example strings where no matter how long you run your program, you need longer to determine yes. So it's undecidable because of that. So we'll come back to that. Let's take a little bit and see if we can write a Turing machine program. We'll start with a nice regular language, 0, 0 star. The first question you're going to want to answer as you design a Turing machine is how many internal states do we need? You know, we need at least one, right? We need some place to start. We need an initial state, but how many other states will we need to be able to recognize this language? Could be one. We need some way of saying final or non-final.
2.
So I would assume we need at least 2 states, one of which says we are currently in a final state that if we move to a halting state from here, we accept.
Well, 2 total, just like starting state of time.
Yeah. So the answer is yes. We need one that's going to represent still searching and one representing kind of finished. So once you kind of identified what the internal states represent, the logic that it represents, then it's time to start thinking about the transitions. So how do we move between these states when we see certain characters? So think about there being something on the tape. We're at the very first position. The first question we should ask ourselves is the character on the tape right where we're pointed a 0? If it's not, then we want to halt in a non-final state. If it is a 0, we want to continue in this, we're going to accept if we finish parsing the string and continue to look at the next character. Continue this process where you look at the next character. If it's not a 0, halt in a non-final state. If it is, look at the next character. And only if you reach the end of the string should you halt in a final state. How do you know you've reached the end of the string? Yeah, you read a blank. The current symbol is a blank. Then you've gone past the end of the string, you know you've looked at everything. So I'm hoping that gives you enough information to be able to construct the transitions. So remember the transitions have the following form. We have 2 things on the left side and we have 3 things on the right side. We have the current state. We have the tape symbol equals a triple. We need the symbol to right. That's the new state. Duh. Now all of my pens are dying. Oh no. All right. I don't know if that's readable remotely. We have the delta. We're going to take the current state and the current tape symbol. And we're going to state the new state that we transition to. The symbol we're going to write at the current position on the tape, and then the direction to move the read write head, which right now is either left or right.
So I think.
Think we have a solution?
He wants that sometimes.
I can give you the first one, because I think it's the easier one to generate. So we have a delta from Q0, reading a 0. So if we see a 0 at the current position and we're in state Q0, we're going to stay in state Q0. We're going to replace the 0 with a 0, the equivalent of a no-op. And we're going to move right to the next cell. The only other transition, there are only 2 of them. If we're in state Q0 and we see a blank, we'll transition to state Q1, which is our accepting state. So one thing that's missing from this is Q1 is a final state. We'll do a no-op on the blank, replace the blank with a blank. And it doesn't matter here if you move right or you move left, doesn't matter. But the idea is if you reach a state and there's no transition defined for it, then you will immediately move to the halt. And the question is, which state were you in when you entered the halt? Were you in a final state or were you in a non-final state? So for instance, if the very first character we read is a 1 and not a 0, there's no transition defined for Q0 on a 1. So we will immediately enter a halt state, but we halted on a non-final state, Q0. So we reject. On the other hand, if we have a sequence of zeros, then we will eventually reach the end of that. And there's no transition defined for what to do when you read a blank from state Q1. And if you move right from a blank, you would expect the next cell to also be a blank. So there's nothing to do from Q1 on a blank, so we will halt. There's no transition rule defined for that. Since we entered the halt from a final state, we accept. So as soon as there is no transition rule defined for the associated input character and state that we're in, we immediately go to the halting state. And the question is, where did we come from? Did we come from a non-final state or a final state? And that is the difference between accepting and rejecting.
Would this accept an empty string though?
It would not, because we start in Q0. So if the very first thing we see is a blank, there's no rule defined. So we'd halt immediately. But since there's no rule defined, we never transition to Q1. I guess that is true though, isn't it? We're in Q0, we read a blank. There is a transition for that. Yeah,
And that's bad.
that is bad.
Except for the string.
Yeah,
So would the fix be Q0 blank equals, oh, like delta Q0 blank equals Q0 blank. Right transition, would that be what we're looking for, so we know that works?
I think you need another state.
yeah, you would need one more state that allows you to say the first character you read needs to be something and not a blank. So yeah, that makes sense. So this would answer the language 0 star, but not 0 0 star. We need that first 0 to be there. So if that first 0 is going to be there, we need to have some way of making sure we read a 0. And the empty string would just be blanks. There's not going to be like an empty string symbol there.
But if the first thing we come upon is a blank, like we're speaking into, correct? That is what
Yeah.
to via our definition that we went into earlier, we have to hit some first character. First non-blank in order to do anything, right? I thought that was like something that we established as the foundation of doing this.
I don't think so, because there will be languages that accept the empty string. If this language were 0 star, we wouldn't want to accept the first character we saw being a blank.
Okay.
Yeah, I'll have to rework this. Yeah, language is 0 star.
Into zero starting just add one line on top, so like Q zero.
Is this would accept the empty string?
Yeah.
And you update the Q, the state code of like Q.
Yes, yeah,
Yeah, I think the only thing to do now, I see, yeah, it's Q, yeah, you have like you want some girl wants to have one and then. The Q man,
yeah,
That's, I guess.
yeah, Q1 blank, Q2 blank R, yep, yep.
Two things, I guess, when we talk about things on the tape, do we have a symbol or some sort of thing for tape? Is it W like we normally do, or is it something different? Or like whatever characters are on the tape?
Oh, we have an alphabet.
Yeah, anyway,
It's defined as part of the definition of the Turing machine.
right, and then, so I guess. The string that could be on the tape can literally be like a blank, I guess.
Yes, it could be just a bunch of blanks. So if we start with the read write head, we know that the assumption we're making is that it is at the leftmost character of the string.
Mhm.
If the first thing we see is a blank, then the only string that can represent is the empty string. That's a good point, though. Other questions? All right, we'll come back tomorrow and do another example. I don't want to dive into another example with 1 minute to go in class. So we'll come to get a little bit more. This will not be on the exam, don't worry about that. Nowhere near enough practice. But I will see you all tomorrow.
Same here, actually, I didn't.
That was the process.
Because then the.
Yeah. Yes. Unless it's clear that, hey.
The whole point of these